Yellow, one and all. Mr. Callan here to help you with Chapter 6, Lessons 1, 2, and 3, putting a lot of lessons together today. But I believe that you know most, if not all of this already. Fractions, whole numbers, and mixed numbers. Goals for today are twofold. Firstly, we want to, let's try that again. We want to convert mixed numbers and whole numbers to fractions, or vice versa, which means, if you've never heard the Latin expression, you may turn it around. Here's what I mean. You take a mixed number, change it to an improper fraction, or take an improper fraction, change it to a mixed number. Then we will also review, because we've already done this, writing fractions or mixed numbers in simplest form. Now, of course, we're going to need these skills because eventually we're going to get to the point where we're going to have multi-step equations with rational numbers. But for today, let's just focus on simplifying. Let's focus on converting back and forth between mixed numbers and improper fractions. Lots of assignment today, folks, but again, I'm not worried. I don't want you to worry. Whatever the date, whatever the assignment number, please go ahead and write the page and the numbers down and come on back when you are ready. So just to re-emphasize, pages 155, 157, 159, most of it, simply write the directions, the problem, and then go straight to your answer. Really, it is only 51 to 62 on the final page where you must show work. You'll see why when you get there. All right, so let's talk. What are mixed numbers and why do we call them mixed? Where does that come from? Well, it's mixed because, quite frankly, it's made up of a whole number and a fraction, a part, a piece, a portion. So it's going to have wholes, it's going to have parts. For instance, the first two examples we have, I see one whole, and then I see 1, 2 out of what appears to be 3, and so the mixed number is 1 whole and 2/3. Below that, you'll see 2 wholes, and 1, 2, 3, 4, 5 out of 6. Therefore, the mixed number, it's called mixed because it's mixed up with wholes and parts, 2 and 5/6. And what are improper fractions? Well, improper fractions are fractions where the numerator is greater than the denominator. In other words, it's more than a whole. So for instance, right here, I'm seeing 1, 2, 3, 4 fourths, 5 fourths, 6 fourths, and 7 fourths. And of course, as you might expect, our goal eventually will be to rewrite these in ways that we can say, okay, well, 7 fourths is the same as saying that's one whole, and that appears to be 3/4. And that, ladies and gents, will be our goal, going both directions, changing improper fractions to mixed numbers, changing mixed numbers to improper fractions. But notice, I never changed the amount of yellow. I never changed the amount of pi. It's the same amount of pi, whether you write it as 7/4 or whether you write it as one whole and 3/4. I often say that you guys can call me Mr. Callan. My nieces and nephews call me Uncle Tim, but I'm the same dude, just different ways of representing who I am. So how do we convert mixed numbers to improper fractions? Now listen, I've heard all kinds of silly stuff. I've heard MAD, multiply, add, and denominators stay the same. I've heard this crazy Concord C. I don't want to hear it. I want you to understand number. So think about it. Why on earth would you multiply that 3 times the 5? The reason is, if you take a look over here on the right, I've colored in 3 wholes, and I've colored in 4/5. Let me just make that a little more clear. Now, why do we multiply 3 times 5? Because we quite literally will be cutting up those 3 wholes into 5 slices each. And so a little disappearing ink here, 1, 2, 3, 4, 5 makes a whole. 6, 7, 8, 9, and 10, 11, 12, 13, 14. That's where the 15 comes from. Not some silly Concord C, not some mad acronym. So we then have 15 pieces, but of course, don't forget to add the numerator. And why is that? Because you still have 4 more slices. So put the 15 slices together with the 4 slices, you now have 19 slices out of 5. Notice at no time did I change the amount of yellow, did I change the amount of chocolate. We still have 3 whole chocolate bars and 4/5 of a chocolate bar, or you could say we have 19/5 chocolate bars, but I didn't change the chocolate bars. We're just writing it in 2 different ways. So if someone were to ask you, Hey, would you rather have 19/5 chocolate bars or 3 and 4/5? You're gonna say, man, that's the same thing. It's just different ways of representing it. All right, your goal, actually, let's try one together. Imagine multiplying 5 fives, that's 25 pieces, but don't forget that one extra piece to make 26. And of course, the fifths does not change. It's still cut up into fifths. So 5 and 1/5 is the same as 26 fifths. Let me give you a minute. I'd like you to pause the video, do the next 3 problems. Come on back when you are ready. 2 wholes, 3 slices each, 2 threes is 6, plus another 2 is 8. So 8/3 is an equivalent fraction. 6 wholes at 4 slices each gives you 24 slices, but that's just the wholes. Add the 3 more parts, you're going to get 27/4. Last but not least, 4 and 5/6 will be the same as 29/6. If you need, pause, rewind, rewatch what parts that you might need or that you're a little weaker on. If they're strong with this stuff, let's keep on rolling. So now let's go the other direction. Let's convert improper fractions to mixed numbers. So 12/7 as an example. Let me go ahead and pull my little highlighter out and let's have a little fun with some purple, shall we? So if I were to, that looks good. If I were to cover in 12/7, remember a whole is cut into 7 parts. That's what that denominator is going to tell us. Well, let me color in 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right. Somebody somewhere might have told you to divide the numerator by the denominator. When you do so, you get that one whole, right? Well, look, that's because one whole part was all filled in. Meanwhile, what's up with the remainder? Well, Mr. Callan, you had 5 parts of the next whole filled in. That's the reason you take the whole number and then insert the remainder as your numerator. Noticing that we're still cut up into sevens, that did not change. The denominator should remain the same. But I have no problem with you dividing. I want you to understand why it works. Why did we divide 12 by 7 and get 1? Because one whole slice, one whole pizza, excuse me, is 7 parts. And then what do we do with that remainder? Well, those 5 extra pieces gets inserted into the numerator. So 12/7 is exactly the same amount as 1 and 5/7, just different ways of representing what they are. Let's go ahead and do one of these together. And I'm not going to draw this one out. I'm going to do the old school method. If I were to take 14/5, imagine dividing 14 slices into groups of 5. Well, in that case, I'm going to have 2 whole pizzas. 2 whole pizzas of 5 slices is only 10 slices, 4 left over, and therefore, put that 2 in the front, the 4/5 is the remaining part. If at any time I ask you to prove it, you should be able to prove it, ladies and gentlemen. So if I were to color in 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, you of course still see the 2 whole parts and the 4/5 left over. All right, so at this point, I'd ask you to pause your video, do the next 3 examples on your notebook, and come on back when you're ready. Let's talk 9/2. If you split 9/2 into 2s, you'd get 4 wholes with one little slice left over for 4 and 1/2. How about 12/3 in the bottom left corner? Well, if you divide 12 by 3, you get 4 wholes with no other pieces. Now, some students might choose to write 0/3, but I really would argue that's not necessary. To be frank, 12/3 is the same as 4 wholes. Meanwhile, 11/4, if you divide 11 by 4, you'd find 2 wholes with 3 slices left over. Once again, if you need, pause the video, rewind. Otherwise, if that's a strength of yours, let's come back. Folks, why are we doing this? Because we need to talk reducing fractions. Again, the essential question for this coming chapter is how can we represent numbers in different ways? You can represent wholes as improper fractions. You can represent mixed numbers as improper fractions. Or you can represent improper fractions as mixed numbers. We can also change the representation of a proper fraction by reducing to simplest form. Now, in order to do so, just a reminder, it would save you quite a bit of time if you could recognize what is the greatest common factor of both the numerator and the denominator. In this case, we could divide both 21 and 28 by 7 and get 3 out of 4. But they're the same amount of pizza. It's just that fourths are bigger slices than 28s. But your belly would not notice the difference if you ate 3/4 of a pizza or 21/8 of a pizza. In like manner, we can come over to number 10, or excuse me, 10 22nds, and we can reduce by the greatest common factor here, which, unless I'm mistaken, I do believe it's only a 2. Let me find out. 10 divided by 2 is 5. 22 divided by 2 is 11. Can that reduce any further? If you're ever in doubt, you can always write the first several prime numbers out. I know we've talked about this before. 2 doesn't go into either, 3 doesn't go in either. 5 goes into 5, but not 11. 7 goes into neither, 11 goes into 11, but not 5. And of course, by then, we're too far and too big. So 5/11ths is simplest form. Now, to get you ready for something more complicated, I will also remind you that you could have expanded this out to all their prime factors. You could have written the prime factorization of both. So for instance, 10 would break down into 2 times 5. 22 would break down into 2 times 11. And naturally, if you have a number divided by itself, any number divided by itself, except for 0, of course, would be 1. So in the numerator, you have 1 times 5. In the denominator, you have only 11. And not surprisingly, we have the same answer. So I would argue that most of you don't need to use prime factorizations for numeric fractions. On the other hand, let's move back into algebraic fractions. And I'll show you two different ways of doing the same problem, 36c to the third d squared all over 9c squared d. Now, once again, can you look at it and identify the greatest common factor? For instance, first just look at the numbers, 36 and 9. Well, I know that 2, nope, not 2, 3 goes into both. Oh, you know what though? 3 is not the greatest common factor. 9 would be. 9 will go into both 36 and 9. Meanwhile, I wonder, can you identify how many C's that they both share? Well, I can argue that they at least both have 2 of them. Yes, there's more in the top one, but we're looking about how many are in common. Then take a look at the D's. And in this case, they would share 1. Yes, there's an extra up top, but the bottom one only has 1. Some of you even write that in for yourself. All right, so let's go ahead now and divide by this greatest common factor. 36 divided by 9 is 4, of course. Now picture c cubed divided by c squared, leaving a single c left over. Sometimes I even cross them out like this and write a new 1 in that place. All right, how about d squared divided by d, where one of them cancels out, leaving us again with a single d. If you wish, you could cross it out as such. Now the bottom gets very interesting. Let's take a look at our denominator, please. 9 divided by 9 is, of course, 1. C squared divided by c squared, all those c's cancel, and d divided by d cancels out. So while you could write 4cd over 1, I would argue simplest form is not necessary to write that 1 in the denominator. A reminder, please, that that big old original fraction, 36c cubed d squared all over 9c squared d, it's the same amount as 4cd. It's just represented in different ways. Now, some of you might be struggling to identify the greatest common factor. And my argument would be maybe by the end of this week, you should be able to handle that and identify the greatest common factor. But students with strong skills can do one way. Student with the strongest skills can do two ways, and as I gave you a little preview on the previous example, you could always write the prime factorization of both. Take a look at the denominator. 9 splits down 3 times 3. Expand c squared with a single d. Again, if you want to write that one to remind yourself that, you're welcome to do it. Now 36, a little tougher. I'm going to come off to the side and do my upside down division just to remind some folks. 2 goes into 36 18 times, 2 goes into 18 9 times, and 3 goes into 9 3 times, and there are all the prime factors. 2 times 2 times 3 times 3. Let's expand c cubed, and let's expand d squared. As previously discussed, any number divided by itself is 1. I don't think you have to write the 1 at this time, but you're welcome to do so. C divided by C is 1. There's another C divided by C is 1. And there's a D divided by D. So if we were to examine the numerator, 2 times 2 is 4, times 1 times 1 times 1 times 1, that's a whole bunch of 4s. Still with a C and a D remaining. Meanwhile, there's nothing down below. Yes, if you wish, you could write it over 1, but I would argue that's not really simplest form. So 2 different methods to simplify. You may find the greatest common factor and divide, as we did at the top, or you may expand out to the algebraic factorization and reduce from there. Let's go ahead, and I'm going to do this one with you. Actually, I would invite you to pause, try it on your own, try it both ways if you can, and then come back when you are ready. So first things first, I'm going to try to identify greatest common factor. And unless I'm mistaken, the only thing that I see going into 39 and 12 is 3. Now, if I were to take a look at the R's and just kind of zoom in on the R's, well, they both share at least one R. Yes, the denominator has 2 of them, but the top only has a single one. So I'm going to go ahead and divide both numerator and denominator by a single R. And then if I were to look again at the S's, there's 3 up top, but there's only 1 down below. And therefore they share at the very least a single S. So 39 divided by 3 is 13. R divided by R would completely cancel out. Meanwhile, S cubed divided by a single S, in my opinion, from what it looks like, leaves S to the second power. 12 divided by 3 in the denominator, R squared divided by R leaves one of those. And S divided by S completely cancels. Now, I always look at the end. Is there any other way that we can reduce? Can anything else go into 13 and 4 other than 1? The answer is no. Does both denominator and numerator share any variables? No, there's only S's in the top, only R's down below. So therefore, that is our simplified fraction. Now, if I were to break this down, 39 is 3 times 13 times a single R times S to the third power. 12 is 2 times 6. 6 is 2 times 3. There's the prime factorization there. R times S. And then we start canceling out. 3 divided by 3 is 1. R divided by R is 1. S divided by S is 1. Leaving us with, in the numerator, 13S squared. 2 times 2 is 4 times R, and again you can check, nothing else will reduce into both. So folks, perhaps you can see why we've combined 3 lessons together, because we've seen it all before. You understand mixed numbers, you understand whole numbers, you understand improper fractions, and we've already done the simplifying piece as well. We're just kind of building up that skill before we get into more algebraic fractions. Remember, please, the only thing you really need to show work for is 51 to 62. All the rest, directions, then problem, then answer. That's what I got, folks. Take care, do well, and let's grow.